Okay, so I want to do this problem. It's 2000 AP Calculus AB number 5, and we're going to start with part A, which is an implicit differentiation problem, of course. So I'm going to start with my xy squared minus x cubed y equals 6. I'm going to replace all the y's with f of x's. Since this is an implicit differentiation problem, then I'm going to take the derivative of both sides. This will require the product rule and the chain rule, so I'm going to do that. The product rule is first times the derivative of the second. You could write out the chain rule, but I'm going to write out what the answer should be. Plus second times the derivative of the first, so that'd be times 1. And that's the derivative of this part. Then minus the derivative of this part, which again is going to require the product rule. So first times the derivative of the second plus second times the derivative of the first. And all that is going to equal the derivative of 6, which is 0. All right, so we're trying to get f prime by itself, so I'm going to distribute everything that I can and sort of clean this stuff up. So I've got x times 2 times f of x, which is y, times f prime of x, which is dy dx, plus f of x, which is y squared times 1. And then I've got minus this stuff, so I'm going to distribute the negative, minus x cubed f prime is dy dx, minus f of x is y, and times 3x squared. So I'm going to get all the terms that have dy dx together on one side. So that's this one and this one. And I'm going to move the other stuff to the other side. So this one and this one. Factor out the dy dx. And then divide both sides to get dy dx by itself. And if you notice, my answer matches exactly what they have, what I was supposed to prove. The only way that I could have gone wrong there if I hadn't actually made a mistake somewhere along the way is that I could have moved everything to the other side, like switched the sides I isolated everything to, which means the top and bottom of my fraction would come out as opposite signs of each other, but that's okay, I can multiply top and bottom by -1. So let's look at part B. Part B says, to find all points in the curve whose coordinate is 1 and write an equation for the tangent line at each of these points. So the curve itself is the original equation that you're given there. And we want to find all the points whose x-coordinate is 1. So if I take that curve and I let x equal 1, that gives me a quadratic that I can solve for y. You would, of course, factor that or do the quadratic formula, but I'm pretty sure that those are the two answers you get. So we have 2 points. One of them is 1, 3, and the other one is 1, -2. And we want to find the tangent line. So we need the point. We've got each of those. But we also need the slope, which means we need to take these points and plug them into the derivative. So when I do it with 1, 3, I'm going to get 3 times 1 squared, which is 1, times 3, minus 3 squared, which is 9, over 2 times 1 times 3, minus 1 cubed. So that gives me 0 over 5, which is 0. So the slope of that tangent line is 0 at the point 1, 3. So if I could write that in point slope form, or I could just realize that's a horizontal line, and so it's going to come out like that, y equals 3. So I do the same process for the other point. So I want to find the slope at the point 1 comma negative 2. So I'm going to plug in 1 for all the x's and negative 2 for all the y's. And this time on top I get, let's see, negative 6 minus 4, which is negative 10, over negative 4 minus 1, which is negative 5. So that's 2. Double check my math there. That looks right. Yep. So then my equation of the line with this point would be y plus 2 equals 2 times x minus 1. And that would be the answer to part B. Now, I need some room on the screen, so I'm going to clear off this work. And as I do so, I'm going to point out that even if you had messed up part A and couldn't get the derivative to match, that's one of the reasons they say show that this is true. So if you have to use it later in the problem and you didn't get this part, you could still do the later parts. So let's talk about part C. We want to find the x-coordinate of each point where the tangent line is vertical. So when we want to find a vertical line means the slope is undefined. Specifically, that you're getting a number of some sort on top and 0 on the bottom, because remember that's what tells you you're getting close to infinity, and a vertical slope is an infinite slope. So what we want to do is take the denominator of my slope and set that equal to 0, because that will make the whole thing undefined. Now, this is going to give us a relationship that can give us a 0 in the bottom. So I'm going to pull out an x. So there's two ways that I could get a vertical line. If x is 0, or 2y minus x squared is 0, or y is x squared over 2. So these are the two relationships that can give me vertical slopes. Now they also have to be on the curve. And the curve itself gives a relationship between x and y. So if I want it to be on the curve and I want it to be vertical, I can do a system of equations with the curve and then each of these two things separately to solve for the conditions that give me a vertical slope and are on the curve. So this is what this looks like. So when I'm looking at the place where x equals 0, I'm going to take the original function, the original curve, and I'm going to plug in 0 for all the x's. This says that 0 equals 6, which is impossible. So since this is impossible, x equaling 0 can't actually be on this curve. So this doesn't give us any answers. It doesn't give us any points on the curve where the tangent line is vertical. In fact, this is an impossible condition. So let's look at the other condition, where y is x squared over 2. Again, I'm going to go back to my original equation. I'm going to plug in for all the y's x squared over 2. So let's see, if I squared this, I would get x to the 4th over 4, and if I multiply that by x, that would give me x to the 5th over 4, minus this times this would give me x to the 5th over 2 equals 6. So these are now like terms, so I can subtract them, and I get x to the 5th over 4, but negative. And now it's just a matter of solving for x. So I'm going to multiply both sides by negative 4, and then take the 5th root of both sides. And before you freak out about, oh my god, there's a 5th root, there's a root of a negative number, remember that a 5th root or any odd root of a negative number actually spits out a negative number. So this is not imaginary, this is actually a real answer. And there you go. That's part That's problem 5 in the 2000 AP Calculus AB exam.